Welcome friends, welcome to my channel. Today we are going to discuss about neighboring group participation, which is a very important topic for JEE main and advanced exam, and also for JAM, UGC CSIR NET and GATE exam. So let's start. So at first I want to talk about there are few experimental observations are made by chemists which are very surprising. Like there are some chemical compounds which are very similar in molecular structure, but their reactivity towards solvolysis are very significantly different. Solvolysis means hydrolysis by solvent. So here we have picked up some examples from Clayden's book. So today we are going to investigate about the reason behind abnormal reactivity. So let's start. So we already know that the simple alkyl halide undergoes solvolysis by simple SN2 reactions. So we are not discussing about it. We all know that for being low electronegative, sulfur is a good nucleophile. So here the nucleophile and the leaving group are in a same molecule. Okay. So there happens an intramolecular nucleophilic attack by the sulfur atom to the beta carbon attached to the chlorine. Okay, which leads to formation of a three-membered ring, which is shown here. Okay, we know that the three-membered ring are very strained, so it always likes to release its strain. So what happens? The solvent, which is water here, it attacks the one of the carbon of the three-membered ring and cleaves the ring, and we got a hydroxylated product. So what is aspect in this reaction? That is a low electronegativity sulfur makes it a good nucleophile. An intramolecular reaction always faster than the simple SN2 reaction, which is bimolecular. And the third is the strained ring, always susceptible to ring opening. So next example is this phenyl substitute alkyl OTS. So in this example, the neighboring group is a phenyl ring, which participates in this reaction. So how it is participating in the reaction, we are going to investigate. Now we all know that the pi electrons are the loosely bound electrons. So in this case, in spite of having the aromatic stability, the pi electrons with a beta carbon. Okay, and the OTS being a very leaving group, we all know that after the attack it leaves. So it as a good leaving group, which leads to formation of a three-membered ring. So now formation of this intermediate, there are two results. These results are aromaticity is lost, which is the first case, and the system always wants to regain its aromaticity. And second is a three-membered ring is formed and it is always strained and wants to release its strain. So due to these reasons, solvent molecules, which is acetic acid in this case, acts as a nucleophile and attacks one of the carbon of the three-membered ring and cleaves the ring, and consequently it regains the aromaticity of the system. So this reaction is faster rather than the simple SN2 reaction of the simple alkyl chain OTS molecule, because the intermediate is formed in this case are more reactive than the simple alkyl OTS structure. Okay, so this phenyl cation attached three-membered ring, this intermediate is being more reactive. It is more susceptible to towards the acetic acid based solvolysis rather than the simple OTS. This is the reason of this fast rate. Now we will talk about this example, which is a bridged OTS structure, which is reacted with acetic acid, which is a solvent in this case, and as well as the reactant. So how this reaction proceeds? So here what happens, that is like the previous case where the pi electrons acts as a neighboring group and acts as a nucleophile, here also the C double bond C attacks the bridged head carbon, and the OTS being a good leaving group, it leaves, leading to formation of a positively charged intermediate. Okay, so now as this intermediate, some bonds are forming and some bonds are cleaving simultaneously. So due to this electron density at the one side, the acetic acid group, which acts as a nucleophile, attacks from the other way around to minimize the electronic repulsion. Okay, so we get back the substitution product. So for clear understanding, I have picked up this molecular orbital diagram picture from the Clayden's book. So in this diagram we can see the orbital picture of the pi orbital and the sigma star orbital of the carbon OTS bond. Okay, so we can see that there is a bonding interaction between the pi orbitals and the sigma star orbitals of this carbon OTS bond. So we know that if there is bonding interaction between the two molecular orbitals, so electron density can be donated from one orbital to another orbital. So here the electron density from the HOMO of the field pi orbital can be donated to the sigma star orbital of the carbon OTS bond. So we know that if sigma star orbital of a bond is populated by electron density, then that bond will be cleaved. So in this way, from this molecular orbital explanation, we can say that this is how the neighboring group participation of this pi orbital occurs in this bridged structure. This is a very interesting experimental observation where the stereochemistry of a molecule affects the rate of reaction. So we can see that the diastereomere reacts with acetic acid to give same product, but reaction 1 is more faster at almost 670 times faster than the reaction 2. So let's see how it works. So we can write the planar cyclohexane substituted cyclohexane structure in a chair form where the OTS and acetic acid are in a empty conformation. One is up, one is down. So we can write this chair conformation, which again uh, equilibrated with another chair conformation through real flipping, where the both groups are in a diaxial form. We all know that the diaxial form is less stable than the diagonal form, but the diaxial form is the orientation of the attacking leaving group, and the attacking nucleophile and the leaving group are in a perfectly anti to each other. So this conformation is perfect for the nucleophilic attack. Okay, so the in spite of being less stable, but due to the reaction condition, the less stable conformers are the most reactive in this case. So reaction occurs through this less stable conformer, and as we can see that the acetyl and lone pair attacks the carbon and OTS group leading to formation of a cyclic compound, and which is quickly clipped by the acetic acid molecule which is in the solvent medium. So leads to form a diaxial ring opening, which is all again a less stable conformer due to its diaxial form. So by ring flipping, it quickly reverts back to its diequatorial more stable form. So here we can see that the acetic acid acts as a neighboring group and helps in the substitution reaction. Due to this reason, the reaction occurs faster than the simple SN2 reaction. Let's take a look of the other conformer. In this case, the cyclohexane structure where the OTS and acetic acid both are the above the plane. So we can draw two possible conformers which are more likely on the same stability. So we can draw either of the conformer, but we can see that in any of the conformer, the attacking nucleophile and the leaving group are not in a perfect orientation for the nucleophilic attack. Okay, so here the neighboring group participation is arrested, but in spite of that, there occurs a simple bimolecular SN2 reaction. Okay, which in this case the acetic acid simply occurs simple SN2 reactions and cleaves the OTS. So we get as the expected product. This for this reaction, this is slower than this previous diastereomere one. Now this is also an evidence of the neighboring group participation where a chiral alpha halo acid reacts with NaOH. The reaction proceeds via simple SN2, and we all know that in the simple SN2 reaction, if a chiral molecule undergoes SN2 reaction, inversion occurs at the chiral center. So there is nothing to discuss. Okay, so what we will discuss is the next case where the neighboring group participation occurs. So let's start. For the second reaction condition, we can see that in presence of silver ion, the reaction gives a retention in configuration. So we like to understand what is the reason behind it. So we all know that the silver ion is a soft acid according to Hartsoft acid base theory. Okay, so it likes to combine with a soft base. So we all know that bromine, due to its larger size, okay, low charge density, it also acts as a soft base. So Ag plus quickly binds to bromine and by attached to bromine makes AgBr thing a good living group. So after the deprotonation, carboxylic acid becomes a very good nucleophile and attacks its alpha carbon, and in this course the AgBr molecule cleaves, leading to formation of a three-membered oxygen-based ring. So due to an oxygen-based three-membered ring, it is very unstable and always looks forward to cleave to release its strain. OH minus, which is in the reaction medium, cleaves the three-membered ring and gives a final hydroxylated product. So here, two times nucleophilic attack occurs on the chiral carbon center. So when the first nucleophilic attack occurs by the carboxylate anion, there occurs an inversion, and second time again the reaction medium base attacks the chiral center, again an inversion occurs. So due to this simultaneously two-time inversion occurs, so there is original conformation, which is the retention in configuration, is achieved.